Welcome to qnawire.
Okay, let's go ahead and start solving this problem. So the question basically says, um, you have a surface S that is a sphere. It doesn't matter what the radius is going to be. And F is a vector that satisfies Stokes theorem. So we at least know that the double integral of S curl F dot ds exists. Okay? So because it satisfies Stokes' theorem, we know that it is equal to the line integral of f dot dr. Now, we know that we're dealing with a sphere. Now, this is the very important part that I would like you to understand. The question is asking us to show that the integral is always going to be 0. How does that happen? So let's take a look at it. First, let's just draw the sphere. I'm just going to call it radius r. Okay, that's the top hemisphere. Now, right now, I am just going to focus on this portion, okay? If we use Stokes' theorem, we can either evaluate the, the surface integral through the double integral, using the fact that this is going to be the normal vector. And then we find the curl F and take the dot product with that, okay? But if we use the line integral to evaluate this thing, the normal vector is pointing outwards, so we know that the parameterized curve C has to go counterclockwise, and we know that the projection onto the xy plane looks something like this. Okay, it's going to be the circle on the xy plane right there. So let's say that the integral of that portion is a. It's equal to a, okay? Now let's take a look at the bottom half of the sphere. I'm sure you already know what I'm going to be doing with this. That is not the best drawing. There you go, a little bit better. Now the normal vector is heading downwards, okay, when we go outwards. And we know that because this is the bottom half, so the normal vector is going to be exactly in the opposite direction. And when we want to do that, of course, the C is also going to go in the opposite direction because of the cross product. We know that it's going to go clockwise because we want the normal vector to go downwards. Okay? So either way, whether you're evaluating the integral using a double integral or a single integral, we know that either the normal vector or the curve C is going to have an orientation that is going to be exactly backwards. But due to symmetry, we know that the integral will be negative, the top one, okay? So because we're evaluating it through the entire sphere, we know that the integral can be classified like this. I can say that let's say C1 is the original red one with the counterclockwise C dot dr. And then the other one, C2, it is going to be the clockwise C. F dot dr. but it's the negative version. Okay, so from there we know that the integral of the entire sphere f dot dr can be represented as the integral of c1 f dot dr plus the integral c2 f dot dr, which we claim that this is going to be the value a and this is going to be negative a, so it ends up being 0. So that's the idea of why when we have a vector field that satisfies um, Stokes theorem, and if we evaluate it through a sphere, the integral is always going to be 0.